This is video 2 on Chapter 6 from your Operating Systems textbook. In this video, we'll be covering both Section 6.2 and 6.3 from your book on deadlock prevention and deadlock avoidance. So the strategy we adopt when we're trying to deal with deadlock prevention is to design a system in such a way that the possibility of deadlock is excluded. The two main methods for these is indirect, in which we prevent the occurrence of one of the three necessary conditions from our last video. And just as a reminder, those conditions are mutual exclusion, hold and wait, and no preemption. And the direct approach, which involves preventing the occurrence of a circular wait, which is the fourth condition for deadlock from our previous video. Now, generally speaking, mutual exclusion can't be disallowed. If access to a resource requires mutual exclusion, then mutual exclusion must be supported by the operating system. Now, some resources, like files, could allow multiple accesses for reads, but only exclusive access for writes. Even in this case, deadlock can occur if more than one process requires write permission. The hold and wait condition, though, can be prevented by requiring that a process request all of its required resources at one time, and blocking that process until all the requests can be granted simultaneously. Unfortunately, this approach is inefficient in a couple of ways. First, a process might be held up for a long time waiting for all of its resource requests to be filled, when in fact it could have proceeded with only some of the resources. Second, resources allocated to a process may remain unused for a considerable period, during which time they're denied to other processes. Another problem is that a process may not know in advance all of the resources that it will require. There's also the practical problem created by the use of modular programming or multi-threaded structure for an application. An application would need to be aware of all resources that will be required at all levels or in all modules to make this simultaneous request. On to no preemption, and there's a couple different ways that we can handle this. If a process holding certain resources is denied a further request, that process must release its original resources and request them again, or the operating system may preempt the second process and require it to release its resources. This approach is really only practical when we apply it to resources whose state can be easily saved and restored later. A good example of that type of resource would be a processor. The circular wait condition can be prevented by defining a linear ordering of resource types. So if a process has been allocated a resource of type R, then it can subsequently request only those resources of types following R in whatever ordering we've set up. Now, as with hold and wait prevention, circular wait prevention can be inefficient, slowing down processes and denying resource access unnecessarily. Now let's talk about deadlock avoidance. This is subtly different from deadlock prevention. In deadlock prevention, we constrain resource requests to prevent at least one of the four conditions of deadlock. In deadlock avoidance, we don't actually necessarily prevent any of those necessary conditions, but we dynamically make judicious choices to ensure that deadlock is never going to be reached. And this does, however, require knowledge of all of future process requests. So we have two approaches to avoiding deadlock. In one, resource allocation denial, if a process makes an incremental resource request that might lead to deadlock, we can deny the process access to that resource. The other option is process initiation denial, which basically just means that if a process might lead to deadlock, we don't allow that process to start. So let's talk about a means of resource allocation denial referred to as the banker's algorithm. Let's first talk about some terms. The state of the system reflects the current allocation of resources to processes. A safe state is one in which there's at least one sequence of resource allocations to processes that does not result in a deadlock, meaning that all of the processes can run to completion. And an unsafe state, obviously enough, is a state that's not safe. And now we come to another one of those pause the video moments. There are some great examples, figures 6.7 and 6.8 in your book on pages 273 through 276. Pause the video and go take a look at those examples of the determination of a safe and unsafe state. Read the accompanying text and make sure you understand how those examples work. So pause the video, and once you've gone and read through that and made sure you understand all that, come on back and hit play again. We gain a couple of advantages when dealing with deadlock avoidance. We'll see in the next video that in deadlock detection, it can be necessary to preempt and roll back processes, which we don't have to do with deadlock avoidance, and it's less restrictive than deadlock prevention. Now, unfortunately, we do have some restrictions on deadlock avoidance, so there's a very particular set of circumstances in which we can use it. The maximum resource requirement for each process has to be stated in advance. Processes under consideration must be independent and with no synchronization requirements. There has to be a fixed number of resources to allocate, and no process may exit while holding resources. And that does it for video 2 of Chapter 6. Our third and last video on Chapter 6 will cover deadlock detection algorithms.